Alrighty, well, welcome everybody and thanks for joining us today. My name is Haley Rambert and I am the Corporate Social Responsibility Manager for Perpetua Resources. And I am joined today with Jean Bosley, our Senior Civil Engineer, who is going to be presenting on the Stibnite Gold Project and our fish tunnel. A little bit about our webinars. If you haven't joined us in the past, there is the option for a Q&A and a chat function at the bottom of your screen. There will also be options for live questions later on at the end of the presentation of the webinar. In that, you can submit them through the Q&A chat, which is two little chat function bubbles at the bottom of your screen. And there are also opportunities throughout so that you can submit them in real time so that we can address them or get to them at the end. And on that, I will have Jean introduce himself and we'll go from there.
Hey, thank you, Haley. As Haley said, I'm Jean Bosley. I'm the Senior Civil Engineer at Perpetua Resources, and I managed the design of the fish tunnel, among other things. I'm also involved in tailings and stream restoration and things like that. But this presentation will cover the tunnel. With that, I'll just jump on right in. I can get the slideshow to work. Okay, there we go. Sorry about that. So anyway, first off, I will give a brief overview of the site. I know many folks who are on this presentation probably have already seen this at some length, chances are, so I won't dwell on it too long, but I think it provides some important context. Then I'll move on to just, what is the fish passage situation right now and what we plan for it to become later. And then we'll dive into some details on the fishway design and have some time for questions or discussion later on. I will probably pause if we get questions coming in as we go. I will probably pause and take them if at a couple intervals, just so I don't have to backtrack slides. But that'll depend on what comes in. So that will head on in. So briefly, the project. Most of you probably know this, but it's in central Idaho, east of Cascade and McCall. And it's one key constraint here about building things at site is it's quite a ways in. We're about 37 miles from pavement or something like that. And, we'll be building an access road to get into the site using, a few present Forest Service roads, but also some pioneered section. And that's a whole webinar in its own right to discuss the burnt log route. But anyway, suffice to say, we're pretty far into the hills and, in some rugged terrain, and we'll get on into some of that a little bit later as we talk about the tunnel and construction. The site, of course, has been mined, been 100 years almost, off and on, and that's left a few legacies. We started out in the 30s, 40s, 50s with some pretty heavy mining activity associated with getting, in a lot of cases, war material. It was a major source of tungsten and antimony for the Allied war effort. Then the site settled down a bit after that, was abandoned and reactivated in the 70s through the 90s. And that was focused really on heap leaching of oxide gold and abandoned again, essentially. And then some limited cleanup efforts were undertaken and left the site where it presently is, where it's, better than it was in 1955 and better than it probably was in 1990, but still with a lot of work to be done. And we think we're part of the solution to that work. Some of the key areas that we really plan to address here is a focus mainly on the yellow pine pit, but I should note there are a few others because they affect what the fish may find once they ascend. So, up in Meadow Creek, you've got a lot of riprap channel, you've got a lot of water quality impacts due to tailings and spent heap leach ore. And then you've got Blowout Creek, which bottom left here runs chocolate milk in the spring still because it was the site of a water dam failure back in 1965 and really still produces a lot of sediment. And we plan to, have a solution for all those, but those are, again, details for yet another webinar. But then the one I focus on here is really the Yellow Pine Pit. So the Yellow Pine Pit was diverted, the river was diverted around that pit first in 1938. And fish have not been able to ascend that spot since. And then in the mid-50s, that pit was abandoned, the river flowed into it and leaves the waterfall that you see there on the upper right image. And that's really the focus of the rest of our presentation here. Here in brief is really the sequence of what happens to Yellow Pine Pit under our plan is, right now you've got a pit lake and you've got a waterfall that's not passable in the upward direction by any fish that live here. In the interim condition, of course, we remine that pit. We take out a lot of the legacy waste that's in that area and remine it and expand it. And to do that, we've got to get the river around safely, and that's the tunnel. And that will connect the fish up to spawning grounds, well in advance of the conclusion of mining. Actually, really from the get-go, as soon as we're built. And then finally, the restoration plan, of course, is that pit gets backfilled and the river restored to a natural condition across the backfill. But as to fish patches, and Haley, anything yet? Probably not yet, but
nope, you're good.
Okay. All right, so we'll move on fish passage wise. Here again is that picture. You've seen it all before, but this is a little zoom in. This is what that pit looked like this sometime in the 1940s. I'm not sure exactly, but this is the pit that existed before the river flowed into it. The tunnel went around. It's into the frame here is where there was a tunnel called the Bailey Tunnel that went around the east side of the pit during the time of this picture, I believe. And then later on, of course, that was all abandoned and the river filled in the pit and started with an empty pit, much like this. And then, of course, since then, sediment's been flowing in. So it's changed a bit to the condition we see now, where you've got a little bit of a delta there on the right side of the image. But still have a really tall waterfall, 80 feet plus tall waterfall that's, again, impassable for any of the fish of interest here, really any fish at all. And then the other thing I'll note, I mentioned Blowout Creek earlier. Right now, Blowout Creek's still making a lot of sediment, and that sediment gets stopped right here. Problem is Blowout Creek, what gets stopped is the wrong kind. All the gravel settles out here, but the sand keeps on going, and the sand isn't necessarily what you want in your spawning gravels. So right now, this acts as a sediment trap for really the wrong kind of sediment. And then during mining, and this is same image as earlier, here's just a perspective of the tunnel with a little bit of a cutaway, 9/10 of a mile long, modest as tunnels go. There are plenty longer ones. And this tunnel will again be built in -1 of our mine plans. So the year before we really start ore production or ore processing. And so within a couple of years of us receiving our permits and building, we'll see fish reconnected to the spawning grounds upstream, which really hasn't happened in about 80 years. The fish have gotten there in the back of trucks intermittently due to stocking programs, but no fish has been able to swim up there in about 80 years since 1938. Here, I just want to show you, again, this is the same pit, same image as before, rotated a bit. This is to give a little perspective of where the pit expansion will lie. And how the sequencing will go. So this is the ultimate pit. This will be achieved in about year 7 of our plan. And then it will start to be backfilled. So we've got to get that backfilled up to the river level before we can conduct the restoration. And that work is what will start in year 7. And here, of course, is the ultimate plan for the site right here. This is what we expect it to look like once we've done backfilling and placing growth media and geosynthetics in some cases. Here's the ultimate plan for that site, and that's achieved in around year 11 or so, ultimately, depending on how the backfilling proceeds. Anything else general yet, Haley? Because then I'll get into the design elements here.
The question is about design elements, so go ahead and keep going, and I'll ask it once you get through it.
Okay, great. And maybe it'll be covered, maybe it won't be in the course of what I'll say next. So next up, again, this will be the design detail bit. So those not technical, bear with me. Hopefully there'll be something for everyone. Yes, first off, one considers, you have a lot of design considerations that specific to our site. Some of them are general in any tunneling project or any fish project, but first off, you have, geotechnical conditions. I'll cover those in a couple slides. We obviously have rocks. It's a rock tunnel for the most part, but you've got to get through some legacy dumps and some glacial till on either end. And then once you're in a rock, you still have to deal with faults. And, the faults that the tunnel goes through are really the major controls on why there's an ore body there. And so we know they're there, and we've investigated them quite well and we know we have to handle that stuff. The next part is, of course, this is on the river. It routes the river around. There's no reservoir. So that's the part that's maybe atypical for what you'd see in a fish passage project, because most fish passage fishways are designed to route fish around a dam where you have a large reservoir and you can essentially control the flow range in the fishway to a very narrow range. And that flow range is a very small proportion of what comes down the river. In our case, the combined facility, the tunnel and fishway combined, have to pass whatever the river gives us. And that can be 8 CFS or that can be 700 CFS of flow rate, depending on the time of year and what kind of snowpack we had. And so that's a key hydraulic design consideration for the tunnel. And while doing all that, we've got to have a fishway, at least, not the whole tunnel maybe, but part of it has to be able to pass all the fish we're concerned with. So 3 species with different swim speeds, and the adult fish have to go up and the juvenile fish have to go down on their way back out to the ocean. So that again puts some hydraulic design constraints on us here. And then, down the line here, we also have to make sure the thing can function and stay functional and safely so. And so it has to be safe for the fish. We can't have fish getting beat up on rough concrete edges or anything like that, or dropping off plunge pools like they really do now coming down that waterfall. And we can't have debris and sediment plugging up the tunnel. It's critical infrastructure for us. We have workers in that pit right there. We can't have it plug, and we have to have it stay functional. So we have to control sediment. We have to control woody debris. As y'all know, fires are common up here. And so trees get burned, trees die, they fall into the river, and we could have stuff, we could have tree trunks coming down the river every now and then. So all that needs to be controlled. And part of that work is we have to have access to maintain it. If for whatever gets past our sediment controls, we need to be able to inspect and maintain the tunnel. And so there has to be an access way down through our tunnel that's dry at least part of the year so we can drive on it. And that leads to some of how we size the tunnel and how we configure the fishway, and we'll get to that next. Geotech, I know we got some contractors in the audience, so I'll cover some of this. Put this slide back in for you folks. So what do we have here? Well, near the portals, and that's the gray shading there, is really soft ground. It's glacial tills, alluvium, legacy dumps near both portals, particularly the north or downstream portal. And then once you get into the rock, you're into Idaho batholith granitic type rocks for the most part, and a couple of major fault zones. You've got the Meadow Creek fault zone near the upstream end, and you've got the Hennessy shear zone near the downstream end. And overall, modest gradient, about 4%, considerably flatter than the adjacent sections of the river because it's a little bit longer route around. And doesn't have a big nick point like the waterfall has. And then, we adjusted that profile a little. You see on the right-hand side there, there's some, shallow overhead cover and overburden on the downstream side. We flattened that downstream part of the tunnel to get underneath that to give us a little better tunneling conditions. And that's why you'll see in a bit, we have a 1.5% and a 4.5% section of tunnel. And then last, it's just out of tunneling economics and the need for an access way. We really settle on about a 15 by 15 section. It's 15 feet wide and a bit of a basket handle shape, 15 feet tall at the center. And that gives us really the best economics for digging. It also gives us plenty of room for an access way and a fishway without being too tight, because the next size down of typical equipment probably be a 12 by 12. But 15 by 15 seemed to be the sweet spot based on our tunneling contractors' opinions. So as far as reinforcement, I mentioned, we got bad rock, a few spots we know we do. We're going through faults. That leads to half dozen support types, 5 of them for rock with varying degrees of rock bolting and shotcrete and eventually structural steel arches for the worst parts. And of course, as the tunnel advances, we'll probe drill and pre-grout as needed to cut off water and stabilize ground. And then, soft ground tunneling is another beast entirely. And for that, we have a pipe or spiral canopy to get through it. So we've investigated the tunnel length. We've drilled along it, and we've drilled into it from above. And generally, we think we have a pretty robust structural design here. The portals, of course, are straightforward. That's a soil nail wall like you'll see at a shopping mall now and then. So anything pop up, Haley?
Yes, so you covered it a little bit, but maybe just reinforcing. So the question was, in regards to the tunnel structure, how you will be taking into consideration the varied geographic, but I would assume the geological conditions at site. So I think you kind of covered that from the 5 components that you just went over. So I think we're
Yeah, we've drilled the tunnel through a variety of methods. So we have, of course, we've also drilled the adjacent deposit because the Yellow Pine pit's our chief ore body, our first pit. So we've drilled a lot of holes related to the pit itself, both for both for geological exploration purposes and for geotechnical purposes for pit wall stability. So we've got lots of core, including oriented core, geotech, all that stuff for the pit. And then the tunnel, of course, is right beside it in the same rock, and actually less beat up rock because all the alteration is generally tends to be east of the tunnel, but as does all the metal. So the tunnel itself has been investigated specifically for the tunnel, and that's included sonic, auger, and core drilling, both vertical holes hitting the tunnel envelope from above, as well as some angled holes, some pretty steeply angled holes, steep from horizontal. So we've gone in 20 degrees from horizontal along raking along the tunnel envelope as well for some really long core holes to cover as much as we could cover from the surface. So yeah, we've investigated all the geotech, most of the tunnel envelope throughout its length with geotech holes of various types, various drill methods.
perfect. We are going to keep going, Gene.
Okay. All right. So hydrology considerations. I mentioned run of the river. This is just the overview plan here. So our project course on the right, this is the pro plan here, or the mod pro plan we're looking at here in the gray shading. Things changed a bit lately, but there's the project plan. There's the Yellow Pine Pit Lake and the general tunnel alignment. You'll see we actually have, we're blessed with an abundance of USGS gauges around. We have 6 on site, one of them right by the tunnel and one right above the tunnel. The one above's got going on 40 years of record at this point. And then we've got gauges down on Johnson Creek. Johnson's got about 80 years of record. And we've got various spots where there are pit tag arrays. So those are transponder arrays that track tagged fish. And then, of course, Johnson Creek has fish traps. So we have some pretty solid data on when fish arrive here and what the hydrograph looks like. And that's the figure you see on the right of, when the pit tagged fish showed up. The right-hand one, that's the Chinook salmon in black. The left-hand one is the steelhead in orange. And then the hydrograph of mean annual flow is in the middle. And you see, the steelhead show up early as the hydrograph's coming up when the snow melts. And the Chinook salmon and the bull trout show up late, really on the tail out when the water's coming back down. And that's a pretty consistent pattern, but it's, can be plus or minus a month, depending on what kind of year you're having. And it's not always just because of flow. So where that leads us is we have to consider, well, when do the fish show up, which fish when, and over what flow range does the fish need to get up the tunnel? And again, this is pretty straightforward stuff because there's fish passage guidance for the whole Northwest that applies here, but we took a little more granular site-specific look at it because we've got the good data down at the pit array by parks. And what we looked at here is originally, right, we said, well, the Chinook are the perceived most important ones here, and they're most endangered. And the fish that must ascend right here are the late arriving Chinook. And that was our original focus here. And this is where you see we shaded. That was our real focus of design here. And knowing that we had a concrete line tunnel of a 4% gradient, would we or wouldn't we get fish up if we hadn't designed it yet? This was early work. What it turned out is we actually covered the whole flow range here and very well. And I'll go through that in a bit. But what we were doing first off was establish over the passage window or over the migration windows, what are the 5th, 95th percentile flow range you have to design to? And that's cookbook design work out of the marine fisheries guidance manuals. So that was the first step, is look at the hydrology, figure out what fish arrive when and what flows do they arrive at, and therefore what flows do you need to design the tunnel to work for those fish. So that was step one. And again, it's run a river, so we handle that whole hydrograph one way or another. Next step was, of course, well, who's done it before? We took a look, and it turns out it has been done before all over the world. Light tunnels, dark tunnels, long tunnels, steep tunnels, flat tunnels, whether intended for fish or not. Fish, especially salmonids, trout and salmon, can make it up tunnels and do. And we did document that. And that was, kind of, again, one of our preliminary steps here. And after that, of course, we got to figure out, well, how do we get them up? Could have a bare tunnel. That wouldn't work very well for us because we're on a river. Fish is not going to get up when there's 400 CFS in a bare tunnel with no other measures. We need some kind of structure. And so we took a look at what those structures could be. I mean, there's weirs, there's slots, there's very detailed, like the Denell passages, the Alaska Steep Pass. We looked at all of them. We even looked at whoosh. For those of you who've seen the Colbert coverage on that, I highly recommend you find it on YouTube. But we looked at the whoosh system even. And so we looked through all of them. And really what really popped up is tried and true concrete weirs or vertical slots. And of course, trap and haul is a fallback. But again, the idea here was to get volitional passage so the fish could swim back up on their own. Trap and haul remains as a fallback plan, but volitional passage being the goal here. Concrete weirs were really the winner, and they performed quite well. And we'll see the whys and how we demonstrate that here next. And how we do is, of course, some what's called computational fluid dynamics modeling. So that's computer modeling. It's been around for a while, but it is now very easy and very advanced because computers have progressed quite a bit. This can be done on a desktop if you don't care too much about how long to wait for answers. But we had McMillan Jacobs, and they're also the tunnel designer, so they deserve some credit here and lots of it. But McMillan Jacobs did the modeling studies, and what we looked at here were, well, you don't model the whole tunnel. I mean, you can't computationally, but you model all the key points. And again, the tunnel is a repeating sequence of one weir after the other. So you look at just a short sequence of them. And what we looked at here as well, at the exits, right? That's where fish tend to hang up in the fishway, where they might decide they don't want to come up. So you look at the X-way exits, you look at all the control structures, and you look at the transitions. I said that the tunnel slope transitions from 4.5 to 1.5%. So you look at that, and then you look at the whole flow range. So we've got those statistically derived flow ranges from our gauge data, where we know we got to get fish up at 8 CFS, which that's a flow depth criteria, right? The water has to be deep enough at low flow. And we've got to get them up, in the case of steelhead, at 239 CFS, where the water has to be slow enough at the high flows. And so you have competing criteria there sometimes. And then, of course, we look at the flood levels, a 500-year flood, which I can reassure folks is the tunnel's 15 feet wide because of other constraints. That makes it oversized for the 500 year. The 500 years a few feet, it's 5 feet deep or something. So we're oversized for the big floods. The real focus is the fish flows here. And here the image there on the bottom that's the control weir. So that's how we get this to work. The killer app here, so to speak, is that control at the headworks keeps the flow range in that fishway pretty low, even though the river range is pretty wide. And we'll show you what that gives us right here. So here's a section, in the section of interest, the middle. You don't look at the right, that's the model boundary and doesn't have valid results, but the middle is where we evaluate here. And that middle is repeated, every 66 feet or 22 feet, depending what part of the tunnel you're in, for the whole length of the tunnel. So what we see here is, at 54 CFS, so that's the high flow for Chinook and bull trout. The river's 54, but the tunnel is only 29. And what that gives us is we've got some speeds here, some velocities of water that you're actually at 6.5 CFS or so over the weir, which is the fast water. Now, if you look down at the bottom here, we have the swim speeds we evaluate against. And Chinook salmon can easily swim 11 feet per second, steelhead 14. Bull trout are the laggards at 2.5. So they're a little more challenging, but we don't design for sustain. You look, because they only have to squirt through a small jet of water here at the weirs. So you're looking really at burst speeds, and the burst speed on bull trout 6.6, and they're again the slowest ones here. The other ones are double and more of that. So what we see here is here's a section through that middle weir. Average through that weir is 6.5. So even a bull trout can get through the middle weir at the highest flow a bull trout would ever experience on their way up the river because of what time of year they tend to come up. So we, again, this was a pleasant surprise for us because we thought, oh, well, run of the river, high flow range, are we going to be able to get the bull trout up? The other ones we're less concerned with because they swim better, but we thought maybe we wouldn't. And it turns out even bull trout, we do well. And if you look at the other speeds there, these kind of velocities are half the sustained speed of a Chinook and less than half the sustained speed of a steelhead. So it's really no challenge at all for the Chinook and steelhead. And that's at the highest flow a Chinook would see. Results similar actually turns out for the steelhead high flows too. So here's another slice here. This is the other part about why we think this will really work well is here's what the velocity vectors look like. So the coloration, or the hot colors, are fast velocities. Cool colors are slow velocities, and the vectors here show you the flow pattern, or the flow direction of a particle at a given point. And what we see here, is wherever you look at in the water column, any one of these slices through the water column, you've got a really large eddy and a lot of slack water in every one of the pools that's formed in between these concrete weirs. And what that means is you don't need a resting pool every 500 feet. You have a resting pool really every 22 feet if the fish chooses to rest. But you also have 100% attraction flow, which is the term for the flow that guides the fish to say, hey, I want to jump here or swim here rather than over somewhere else where the flows might be different. So you've got 100% attraction flow, and you've got resting pools every 22 feet in the steep section of tunnel, and you've got velocities that are, readily achievable by any of the fish of interest. Here's the headworks. I mentioned the control weir. Well, here it is at the highest steelhead flow. At that flow, the reason the velocities stay really low in the fishway is because of this long weir. At these kind of flows, we send most of the water down the access way. Which is scour protected, of course, but we send most of the water down the access way. The river might be 239, but the fishway is only 52 here. So what that means again is that the velocities are still well controlled in the fishway. And here we have, a steelhead flow. So this is spring runoff on the way up to the spring peak, 239 CFS in the river. And we've got bull trout worthy speeds in the fishway, even though, bull trout aren't trying then, but they could if they were there. And then of course, steelhead are the best swimmers of the batch. So there's really no challenge at all for a steelhead to get up during even the high flows in the spring. So Haley, anything? Because then I'm going to jump just into the fishway details here.
Yep. So this is actually the perfect slide to stop on. So okay. Again, in the design and hydraulic models for the tunnel, you talk about juveniles and adult. So this question is specific for Chinook and bull trout. What is the plan to keep Chinook juveniles separated from hungry bull trout? That's right here, here and above. That'll be the next 2 out of the next 3 slides will cover that here. And let's keep in mind too that we don't want to cause predation, of course, right? And we've taken measures to prevent it. We of course can't prevent it once they're outside our area of influence and down the river, and that predation is natural, and those two species co-evolve. So some level of predation is inevitable and natural here. What we don't want to do is make it more than is natural, and we want to protect them as best we can while they're under our control. But yeah, once they're down the river, there's nothing we can do or really arguably should do about it. And if it was determined by the services that hey, we don't want them here at all, bull trout, because they're so much different swimmers than the others, if directed, we could readily incorporate barriers to bull trout. I mean, a velocity barrier for bull trout that was passable by the others should be pretty readily achievable, but nobody's asked for that. As far as our consultation with the agencies,
all three fish are to pass. And really, we get the cutthroat too. I don't talk about them, but Westlobe cutthroat are of interest, and so we accommodate them, but we don't ever sacrifice the three ESA listed species performance for the cuts. So anyway, we'll go through the how here. So this is a fisheye view for an ascending adult, regrettably. So we'll hit the juveniles on the way up. So an adult ascending, first thing they encounter here, bottom right, is there are a series of weirs, rock or concrete weirs in a transition channel that gets you from the end of the really highly engineered fishway back into the river. And that transition channel is 1.5% gradient, same as the lower part of the tunnel. So no challenge to any of the fish of interest here. The river below it is 3 to 7% gradient naturally. So transition channel, series of weirs to keep water depths adequate for all the fish, even at the lowest low flow, and to keep the velocities in range, even at the highest high flow. Again, not much challenge in the big open channel compared to, say, a constrained tunnel. But that's the first thing they see. After that first weir, you've got a big adult resting pool. Now, do they need a rest? Probably not at the gradients in the pool sizes we already have, both below and above within the tunnel. We have the standard resting pool there and the fishway entrance. Now, next to the resting pool, of course, is a barrier to keep the adults from trying to ascend the access way, because the access way is a 9-foot wide, essentially concrete channel. It's going to be going fast and be shallow if it's flowing at all. We don't want the adults to try to head up that and fail and exhaust themselves. So there's an adult exclusion barrier there. It's just a bar screen. And above that barrier is a pool. So any juveniles that happen to go down the access way, because we can't 100% prevent them from doing so, behaviorally, they probably won't try, but we have to assume some will get through there. So there's a juvenile orientation pool there at the bottom. That's for the juveniles that just went for the flume ride to really get their bearings before they have to run the gauntlet of any adults, especially the bull trout that might lie downstream. So that's what goes on there. And then of course you have the fishway that looks, all the same all the way up the rest of the tunnel. The portal structure here and the access ramp, simple enough, right? The portal is just standard, again, soil nail wall like you see a shopping mall development or a building somewhere, or next to a building somewhere on the high side of the cut. So that's the downstream portal. So that's what the adults see coming up. This, of course, the juveniles will be coming down this one side or the other. Here's the inside of the tunnel. Again, there's a partition wall. We keep the flows split. We keep the water in the fishway at low flows, and then we keep the water will share both sides in high flows. The amount being controlled by what lies at the headworks, which we'll cover. You see another image of in a second, but really this is just reinforced concrete weirs. There'll be slip formed where we can for smooth results and good productivity, but there's not a lot to see here, really. This really is a standard run-of-the-mill, fishway weir type technology here. And standard tunnel technology too, right? This is just like forming a jersey wall inside of a transportation tunnel. Then here's the upstream end. This is where the real magic happens, so to speak, is again that control weir sits next to the resting. There's another, again, redundant resting pools because there's resting conditions in all the other fishway pools. But you got the fishway up here. It's about 4.5% slope because this is the steeper part of the tunnel. You've got a fishway exit. They exit into that resting pool. If flow is low, all the water is going into the fishway. If flows are high, some of it's going over the control weir. And that's where we've got pickets to try to keep from having fish go over the control weir. Those will work unequivocally for the adults because of the size of the pickets. We can't prevent the smallest of the small juveniles 100% of the time from going over, and that's why we have accommodation for them down at the lower end. But again, behaviorally, our fisheries experts think really the fish are going to, for the most part, go down the main fishway, even the small juveniles. There's no reason they would want to be over the flow that goes down the control weir, and the time of year they descend shouldn't be at the maximum kind of flows. And then the next thing up, we have a debris barrier. That's just a big bar screen. It's angled to allow access from one side to clean it off if we do get a lot of debris hung up there. And that's to catch the logs and the large woody stuff and floating debris that comes down. And that's bar screen size standard, Marine Fisheries Service size bar screen to pass the Chinook adults through it, which are the biggest fish of interest here. And then above that is where we catch the sediment. It's a mountain river with a steep watershed with some erosion. We will have by this point fixed blowout creek, so we won't have that extra slug of sediment. But we've sized this for long-term function to catch any sediment we expect to see even in a big year here. And so we have a long reach of very flat gradient that will settle sediment. And then we have that sump pit there on the left that will catch the big stuff probably before it gets into that flat reach, and that will catch most of the sediment and provide us a really focused spot to clean it out, which we'll plan to do every year at least once, and maybe more than once a year. And we looked at sediment loads and sediment transport and what we can expect. And the clean out intervals is annual, and the clean out duration, and we're talking a work shift or 2 or 3, depending on the kind of year we get with the equipment and manpower we'll have. And so here we are at the end. I didn't cover the detail here, but of course we have a lot of solutions in the works for some of the other problems in the watershed, so the fish have something to find when they ascend the tunnel. But the key points of the tunnel is we're looking at volitional passage for the first time in 80 years, right at the beginning of the project, and that'll give us a jump start on what we'd have to otherwise wait for if we waited till the backfill had occurred. And then once we do finish the project up, and before we've ever left site, 2 more pits to mine, and we'll be starting the backfill Yellow Pine pit and get the river restored before we're even finished completely with the other pits. And that will lead them to a lot of, again, there's a lot of habitat restoration in the plan as well that it's a whole nother webinar that they get once they get upstream. And lastly, we've got proven tech here. This is standard conventional stuff. It may be put together a little differently in a different order for different reasons, but we've all got pretty high confidence that this thing should work both in the short and the long term. And I think we're down to Q&A.
Perfect, Gene. So we have one more question that has come in. What is the plan for the fish tunnel? Even on this slide, it has for volitional fish passage is temporary through the tunnel. What happens to the actual tunnel during closure? Does the tunnel get backfilled? Does it get?
No, we don't backfill full length. We seal the ends. So, and you'll seal the upstream end, make sure, remember the river's right there. So that control weir will, and the fishway weirs will provide part of that closure where we will build those up to make sure we have, that's one seal to keep river water and alluvial groundwater out. And then we'll seal inside the tunnel. When get in a few diameters in and build a wall basically, or use a foam product. It's 6s, it's really which one is going to work better. And then backfill from there out. And so we'll have the whole transition zone there will be sealed, then backfilled out, and then restored, with normal surface reclamation methods. And then the same general idea on the downstream.
Perfect. And then one more question. In the tunnel design, there between the variation of the 4.5% and the 1.5%, how many roughly number of weirs and resting pools are there within the tunnel itself?
Oh, I'll have to calculate that. It's 100 or 2. You've got 9/10 of a mile, and most of the tunnels, the 4.5. You see that transition break at 1.5 is down near the other end. So if you just assume at 4.5 everywhere, 216 weirs. I think the real number, because of the short section at 1.5%, I think it's 180 or 190, but round numbers is about 200 of them.
Perfect. Well, it doesn't look like we have any questions that have come in besides those ones. So there is the opportunity. So we've recorded this webinar that we will post it online following today. There's also the opportunity, if you have any questions afterwards that maybe you didn't get to ask or get to today during our presentation, you can go ahead and email us, and we are more than happy to respond.
Yeah, we'll do. And yeah, thanks for lending me your ear. And we also have other webinars, and then I believe all the prior ones are recorded too. So for other topics of interest, they're up there on YouTube and linked from our site.
Perfect. Thank you, everyone.